Okay, so now let's continue with our lecture on the quantum mechanical harmonic oscillator. So this is part 2. And at the end of last lecture, we were at the point of considering a trial or guess wave function solution to the Schrodinger equation. So we end up with this Schrodinger equation that has the sort of second derivative term, and it also has an x squared term that results from the Hooke's law type potential, the parabolic Hooke's law potential. And we need to have a function that when we take the second derivative of it, it's going to give us back some kind of x squared term. And then we can sort of work from there and try to adjust our function to fit the differential equation. Okay, so if this is our wave function, psi equals e to the minus a x squared, again, where e is Euler's number, it's the base for natural logs, base e natural log. Then if we take the first derivative of this, right, psi prime or d psi dx, we're going to have to invoke the chain rule. And let me just talk a little bit about the chain rule and how it applies to these kinds of problems. Basically, if you have a function f of g of x, some sort of composite function, where you have some function of x inside of another function, and that's what this is, right? You have an exponential, that's a function of x. But then the argument inside that exponential, instead of just being x, it's a function of x, it's ax squared. And so if we want to calculate the derivative of that, according to the chain rule, it's df dg times dg dx, which seems perhaps a little bit vague, but what we mean here is that in this case, f is e to the g, and g is equal to minus ax squared. Okay, so we're going to have the derivative of the exponential times derivative with respect to g, and then times the derivative of g with respect to x. So that's going to give us the first derivative of the exponential is just 1, right? The derivative df dg, and so or 1 times e to the g, and in this case we might as well plug g back in, so we get e to the minus ax squared, and then times dg dx, which would be minus 2ax. Okay, and we would probably want to put that in front, usually put the more complex function towards the end of our expression. At the beginning we have constants, and then we have maybe powers of x, and then more complex functions such as exponentials or sines and cosines. So in the typical form, we have minus 2 ax e to the minus ax squared. That is the first derivative. Now the second derivative is going to be a little bit more complicated. It would be the derivative of this expression. That's going to involve a product rule and a chain rule. And so the product rule, we're going to split this up into, sort of two functions that are the product of each other. And so applying the product rule, we would get, let's say, take the derivative of the first part with respect to x times the second part plus the first part times the derivative of the second part. So that's the product rule, which is dx fg is g times df dx plus f times dg dx. Okay, so then applying that, first let's take the derivative of the first part there, so we get a minus 2a times the second part, not the derivative of it, right? We took the derivative of the first part, and so we get e to the minus ax squared. Then we get a minus 2ax times the derivative of e to the minus ax squared, which we already saw up there is minus 2ax times e to the minus ax squared. And so we get times minus 2ax e to the minus ax squared. And again, this is a sign. This isn't saying that we're subtracting. It's just telling us what the sign of that term inside parentheses is there. So then multiplying those signs together, we get, let's see, well, first of all, let's bring forward minus 2a e minus ax squared. Then, and essentially we take in minus 2ax and we square it. And so that's going to give you plus 4a squared x squared e to the minus ax squared. Okay, so that would be applying the combination of chain rule and product rule to get the second derivative. And if we sort of look at this, it looks like a function of this sort of type, right, with where we do some change of variables, we set a equal to some specific collection of constants related to, say, h bar and k and mu and so on. That's such a, and then maybe we need a factor of 2 or something to get things to cancel out right, or a factor of a half. Then this could be a possible solution to the Schrodinger equation. So instead of trying to derive that, I'm going to start with sort of the solution, and then we'll show that the solution works. We'll show that when we plug this solution in, it has this form of psi equals e to the minus ax squared. It's that sort of general form. It's slightly different, but it has the x squared in the key parts, the exponential and the x squared. Those are the same. Just fiddling around a bit with constants. That this can be a solution to the Schrodinger equation. So let's, in other words, when we take the second derivative and toss in the potential, we end up with an eigenfunction of the Hamiltonian. And in other words, a solution to the Schrodinger equation. Okay, so then to do that, we define a new constant. We'll call it alpha. It's k mu over h bar squared to the 1/2. And we define our wave function, our trial wave function, as e to the minus alpha x squared over 2. Now, because this has this divided by a factor of 2 there, it slightly changes the way the derivatives work. D psi dx is going to be minus alpha x e to the minus alpha x squared over 2. And d squared psi dx squared is going to be minus alpha e to the minus alpha x squared over 2 plus alpha squared x squared e to the minus alpha x squared over 2. In other words, let's see, we can factor out our psi here. Since this is psi and this is psi, then this gives us equals alpha squared x squared minus alpha psi. So then if we plug this into our Schrodinger equation, first of all, let's write down what our Schrodinger equation is. Again, the Schrodinger equation is minus h bar squared over 2 mu d squared psi dx squared plus 1/2 kx squared psi equals e psi. Okay, that's the Schrodinger equation. Then we're going to see if this psi that we've come up with here is actually a solution. So first of all, let's go in and we can plug this result here into d squared psi dx squared. So that's going to give us minus h bar squared over 2 mu alpha squared x squared minus alpha psi. All right, so we got rid of the derivative by replacing it with our result that we got there for the second derivative of psi. So we plug that in, and then we have our plus 1/2 k x squared psi equals e psi. Okay. And we know that from our definition of our constant, we know that alpha squared is k mu over h bar squared. So we can plug that in to we can combine these two results, and that's going to give us see, some things will cancel there, right? We've got a mu in the numerator, mu in the denominator, and see, k doesn't cancel, but the h bar squareds cancel, and so we get equals minus 1/2 k, sorry, that's supposed to be a half, kx squared psi, and then we have this alpha here, and it still is going to have the factor of h bar squared over 2 mu, so we'll keep that for now. Alpha h bar squared over 2 mu psi plus 1/2 kx squared psi equals E psi. And we notice that because of the choice of our function and that variable alpha and the way things come out, these two terms cancel. So then we get alpha h bar squared over 2 mu psi equals E psi. Great. So now we've determined the, right, we've performed the second derivative. So that's all taken care of. We've done some cancellations and we end up with, it looks like a solution to our eigenvalue problem. Such that, and that's what we're trying to do, is find what the energy is in this Schrodinger equation. And it ends up being, of course, we have to find the energy and the wave function simultaneously. Right? And so we made a guess at the wave function and we found that it gives us that when we take the second derivative and put in the potential, we get back some collection of constants times the wave function that we started off with. And so it's a solution to the Schrodinger equation. So then from this, of course, by sort of inspection, our energy, and this isn't a trick or anything, this is just, you know, algebra at this point. It's alpha h bar squared over 2 mu, and alpha is k mu over h bar squared to the 1/2. The square root of all of that. And we get that some things partially cancel. We get that we end up with k to the 1/2 power. We have a mu to the 1/2 in the denominator and a mu to the first power, just a mu in the denominator. So that's going to give you a square root of mu in the denominator. And we have, let's see, h bar squared to the 1/2, so h bar in the denominator and h bar squared in the numerator. And so putting all that together, we end up with h bar over 2 square root of k over mu. And so we can also go back to our definitions of frequency and angular frequency, so nu and omega, from the classical harmonic oscillator. In order for those concepts to mean anything, it doesn't mean we're imposing classical harmonic oscillator. These are just frequencies from the classical harmonic oscillator. They may or may not be useful. So it turns out, right, that nu is equal to frequency, right, from the sort of classical picture of frequency is 1 over 2 pi square root of k over mu. And so by inspection, since h bar is h over 2 pi, then our energy is h nu over 2, where we've used our classical oscillator frequency nu. Or we can also say that it's h bar omega over 2. It's supposed to be an omega. looks a little bit more like an omega. Okay, lowercase omega. So that's, and now have we solved the Schrodinger equation? We have one solution. There are other solutions to the Schrodinger equation. In fact, there are other harmonic oscillator states. It turns out we can try another one. Psi equals x e to the minus alpha x squared over 2. We can plug that in, take the second derivative of it and everything. It also gives a solution, but at a different energy. 3/2 h nu. And you can tell by looking at this, so e to the minus alpha x squared over 2, that's this bell curve shape, this Gaussian bell curve shape. If you multiply it by x, then you end up with a function that changes sign at x equals 0 and is 0 at x equals 0. So this has what we call a node, and we, I believe, talked about nodes in the particle in a box. So this function up here, the previous function has no nodes. This one has one node. And there is another one that has a second order polynomial in x. It has an x squared minus some constant squared. And so it turns out that there are a series of functions. We're not going to go into details on them because there's really no point in memorizing the full, well, it's impossible to memorize the full set of functions. You would be supplied what those functions are on, say, on an exam. So there's, and they're easy to look up in tables and so on. So, however, being able to show that a given function is an eigenfunction in the Hamiltonian, that would be a skill that would be expected of you. Anyway, so enough from sort of what's expected on homework or tests. Let's get back to these energy levels. So it turns out that there's an infinite series of states, and they're of states or wave functions. And you'll notice we haven't actually normalized these wave functions yet. And again, I'm not going to worry too much about the normalization constants. There's not that much information in them. It's sort of just accounting at that point. I think it's the overall shape of the wave function that's more important than the actual constants that are out in front. Anyway, so we end up with a series of solutions. We'll call them psi sub v, and it's equal to some normalization constant that's going to be different for each state. So we'll call it n sub v, that's our normalization constant, times something that unfortunately is called h sub v, because these are what are called Hermite polynomials. So I know we also use h for Hamiltonian, but this h sub v is a Hermite polynomial, and e to the minus alpha x squared over 2. And the Hermite polynomials are polynomials in x, but there's also an alpha that shows up in there as well, and so we define We define xi as a sort of dimensionless x, alpha, so alpha to the 1/2 x, and the Hermite polynomials are given by this h of xi we have h0 is 1, h1, so these are going to be polynomials in xi, so h1 is 2 xi, h2 is 4 xi squared minus 2, and so on. And there's actually a recursion relationship where once you have 2 of these, you can generate the whole series. And we won't go into that. Again, it's sort of we don't want to go too deep into every little nuance that we have to sort of pick and choose. But nevertheless, that's, you can look that up. It's fairly straightforward to find. Okay, so that's our wave function, and I haven't even given you what the normalization constant expression is. Again, we won't necessarily worry about that. The first few of this series are provided on equation sheets during an exam, that sort of thing. And then our energy, but the important thing is our energy levels, EV. So V, I haven't talked about yet. V is our vibrational quantum number, and it's h nu V plus 1/2, where V is an integer, but it starts at 0. So it's a list of integers starting at 0. And that's just because that's the way that the math works out for this. Of course, you could make a slightly different expression like this. It'd be a little bit more complicated to work with, and have V start at 1 so that it would be consistent with the particle in a box case. But in general, we have to keep track of the fact that the list of quantum numbers sometimes starts at, say, 0, sometimes it starts at 1. It depends on the system. There's no universal rule. It's just something you're going to have to deal with for each system. And so what does this look like? Essentially we end up with, if we plot energy along the y-axis and we make an energy level diagram, and if we start at E equals 0, so we'll just use a dashed line because that's not an actual energy level of this system, then we'd have our first state would be at E equals h nu over 2. The next state would be h nu over 2. h nu over 2, and so on. So we have this spacing. This is often important for spectroscopy. In spectroscopy, you're absorbing a photon and the energy of a photon corresponds to the energy difference between some energy levels of the system. So you absorb a photon, promoting the system from one state into another. And so these spacings between states are important. So this is a little confusing, and it's worth talking a little bit about this, in that perhaps in a prior courses, there might be just sort of one energy, right? Whereas in this system, there are a lot of different energies going on here, right? There's a series of energy levels, and then if you're absorbing a photon, of course, there's some rules that say, you know, certain transitions between one quantum number and another are allowed, and so then there's the energy of the transition, and so just assuming energy is energy is going to be can give you the wrong answer. You really have to keep track of where are you and where is energy, how is energy being conserved, and you know, there's energy going into the system, and then what happens to that energy. So you have to keep all that in mind. Anyway, so the spacing between energy levels is going to be, as you can see, between h nu over 2 and 3 halves h nu. That spacing is h nu, the spacing between any two adjacent levels. And so you end up with this evenly spaced ladder of states. And comparing and contrasting with the particle in a box, in particle in a box, it was not an evenly spaced ladder. The spacing between the rungs of the ladder gets bigger as you go higher in quantum number. In this case, evenly spaced. And what else to say about that? I believe I already mentioned V is the vibrational quantum number. We have this evenly spaced ladder of states. Another thing that we should consider is, what is the minimum energy of the system? The minimum energy of the system is h nu over 2, where nu, again, is related to the square root of k over the reduced mass. Now, then it's interesting to be able to compare and contrast to the classical version of events. And so for a classical harmonic oscillator, right, for just a particle in a spring, the minimum energy for the system, again, using the same sort of zero of energy that we use to define our potential energy curve, such that potential energy is 0 at x equals 0 at the displacement equals 0. Then the classical minimum is 0. Kind of like in the particle in a box case. Classical particle in a box, the minimum energy is 0. It's a particle at rest inside the box, right? And in the particle in a box case, yeah, this shows that there's this confinement energy, and so yeah, so in this system there's sort of a confinement energy too, although it's not completely confined. There's a potential. There's not an infinite barrier. So we use a slightly different terminology. We call this the 0 point energy. And there's supposed to be a space between those two words. It's the 0-point energy of the vibration. And of course, 0-point energy is one of those terms that shows up in sci-fi and in scammers who want to sell you a device that's going to extract the 0-point energy from everything and give you free energy. But yeah, so it's a concept that shows up in the harmonic oscillator, and it's kind of related to this concept of a confinement energy, but it's for a different set of forces. And this has the somewhat disquieting effect, very much analogous to the particle in a box case, where molecules with vibrations are never really fully at rest. Not only are they translating back and forth like a particle in a box, even the vibrations within the molecule have some kinetic energy associated with them, some 0-point energy. And so that's so even at absolute zero, molecules undergo some sort of vibration. There's some motion occurring. In the quantum realm, nothing is ever completely still. And this is a known phenomenon. If in fact you try to map, do classical simulations of molecules using the potentials, you can get some approximations of the behavior of, say, liquids or ideal gas molecules. But if you don't include a correction for the 0-point energy, you'll get answers that are way off in many cases. And so, so this 0-point correction is something that we have to apply if we're trying to approximate a quantum mechanical system using classical Newton's equations type molecular dynamics simulations. And this is well known in that field. Now let's move on to what do these wave functions look like. Again, I just kind of want to sketch them. So the v equals 0 state roughly looks like this kind of bell curve. So we have x equals 0, and it's this kind of curve that's symmetric about the x equals 0 axis. The v equals 1 state has a node. We try to sketch that. Again, this is proportional to x times e to the minus alpha x squared over 2. And so that extra factor of x gives us a node. It forces the function to go through 0 at x equals 0. And then, of course, at larger x's, it sort of eventually decays exponentially, just like in the other case. And you end up with this somewhat symmetric, but kind of flipped about the psi equals 0 axis, this kind of somewhat symmetric function that has a negative lobe and a positive lobe. And our v equals 2 is going to have 2 nodes. So it's actually not going to go through 0 at x equals 0. It's going to go through 0 a little bit on either side. And then sort of trail off exponentially at large x and very small x, so x in the minus x direction, and so on. And so, v equals 3 is going to have 3 nodes. It's going to have one in the middle and one on either side of the origin. And another thing that's interesting about these functions is I said they're symmetric. There's something called even symmetry and odd symmetry of functions, and this is something that sometimes comes up in integrals involving sines and cosines, so it's maybe something you've run across before, that cosine of x is an even function and sine of x is an odd function. So if we say that if your function of x is equal to function of minus x, then we say it's an even function. And if f of x is equal to minus f minus x, then we say it's an odd function. It has odd inversion symmetry. So if we replace x with minus x, evaluate the function, do we get back the same function or do we get minus sign times the same function? If we get back the same function, it's an even function. If we get back the minus sign times the function, then we have a function with odd inversion symmetry. And of course, not all functions are either even or odd. Some functions are neither. However, a lot of the functions that we end up with in quantum mechanics, particularly for these simpler problems, are going to have a lot of symmetry, and so we can take advantage of this even odd symmetry. And in fact, as we saw in the sines and cosine case, and we're sort of repeating it here, the integral of the product of an odd and an even function is 0. In other words, the integral of an odd function, and let me add something to this. If you take an even function and multiply it, so I probably should have said this before this, an even function times even gives you an even function. Even times odd and odd times even is odd, and odd times odd equals even. Now, the integral of an odd function over all space, which would also be true for the product of an even and an odd function, the integral of that function over all space is going to be 0 because there's going to be positive lobes and negative lobes, and because they're symmetric, they're going to exactly cancel. Assuming that your function is well behaved at x equals infinity or is somehow truncated before x equals infinity. So in this case, we've got exponentials. They die off nicely. They go to 0 at x equals infinity. So this will be a useful rule, and you can use this rule to show that, say, the product of the v equals 0 wave function and the v equals 1 wave function, that's going to give us an odd function, and the integral of that odd function over all space is going to be 0. So therefore we know that v equals 0 and v equals 1 are orthogonal. And similarly for v equals 1 and v equals 2, and so for any two neighboring states, they're orthogonal. Now it's trickier to prove. You have to engage in some recursion relations and so on. It's trickier to prove that v equals 1, or say v equals 0 and v equals 2 are orthogonal. That's because they're both even functions, but it turns out that that product is also that these wave function that v equals 0 and v equals 2 are also orthogonal. But the proof is a little bit trickier. So we know that some of these states are orthogonal to each other, and it can be shown that the other ones are. Again, we don't want to necessarily go into all of the possible details. There's a lot of directions we can go. However, I do want to sort of show the important concepts that are going to continue to that will be recurring themes, and that help us to make predictions and make some observations and connections. And so let's take a look at let's plot the energy levels and potential energy, so our V, in the same plot. See, so we have E along the vertical axis here. We've got X, and we have X equals 0 here. Draw a nice dotted line here so we know where the sort of midpoint is on our graph. And the potential energy is going to look like a parabola. Nice continuous curve. V equals 1/2 kx squared. And then on top of that, we can plot our energy levels, our quantum mechanical energy levels. We'll just do the first few here. So that's h nu over 2 and 3h nu over 2 and 5 h nu over 2. Okay, so we've got our energy levels, and I just decided to stop the curve where the energy level meets the potential energy curve. I just arbitrarily decided that. And of course, our general function is h nu times v plus 1/2. Okay, and then I'd like us to consider something that I sort of hinted at having the lines for the energy levels stop where they meet the potential energy curve. And so let's consider that for a minute. What happens, or what's the situation when EV equals V. So let's say we have a system in a particular energy level, E sub V, so say E equals H nu over 2. And then let's consider what's happening at this point here and here and here, right, where the two curves meet. What does that position tell us about? So if we take our system and we sort of momentarily ignore quantum mechanics and we pull on our on the molecule until the energy is until we meet we set the position equal to the energy of the corresponding quantum mechanical level. So if we think about this classically, if we start off with the system classically with the energy of H nu over 2, whenever E equals V, that corresponds to something that's called the classical turning point. That's the point at which, again, for a classical system, the particle attached to the spring sort of stops at that point and then turns around. So you get this oscillatory behavior where it stops at the classical turning points. You have velocity as at a maximum at the bottom at sort of x equals 0 at the bottom of the potential well, and then it again reaches another. It stops again at the negative classical turning point. There's going to be two of them, and so it may be useful to consider. Well, we can do a little bit of algebra, right? So let's see if we can find out what an expression is for the classical turning point, and we'll see we'll get similar expressions later for, say, for the hydrogen atom. So this is an exercise that we'll do more than once, but for different expressions for energy and for potential energy. So finding the classical turning point in terms of x at the classical turning point, that basically you would set E equals V, and of course you replace x with x CTP if you want, to keep track of sort of what we're doing here, and then solve for x. Right, that will tell us the position corresponding to the x-axis position corresponding to sort of where these classical turning points occur. So if we do that, set equals to V, solve for x, we get E is, of course, H nu times V plus 1/2, and we get equals 1/2 k x squared CTP, and of course we can do a little bit of simplification and move things around and come up with a general expression. Let's look at just the V equals 0 state, or the V equals 0 case. Then we have H nu over 2 equals 1/2 kx squared, classical turning point. The 2's cancel, and we get that the classical turning point is the square root of H nu over k. And there's probably some additional simplifications one can use, because nu is 1 over 2 pi square root of k over the reduced mass mu. And so there may be some additional, so there are different forms of this depending on exactly how you intend to simplify. All right, well, so that gets us part of the way through this particle in a box. We'll look a little bit more at this curve, or at this classical turning point situation. And then we'll also move on to some expectation values and consider the Heisenberg uncertainty principle associated with the variance of the position and momentum. So that will be in the next lecture.